Welcome back to yet another video of A2Z studies. Today we will be starting off with force for ICSE class 10. We will have a just quick recap. Force can be classified as push or pull. Whenever we pull a body or push a body, so force is getting applied. What can be the effects of force? It can make a stationary object move. For example, here we have a golf ball. If we hit it with a club, the ball was at stationary, it will start moving in this direction. It can stop a moving body. Whenever a bowler or a fielder catches a ball, he is stopping the ball. It can change the speed of a moving object. If we push the pedal with a force, then the cycle will move with a greater speed. It can change the direction of a moving object. We all have watched in the game of cricket that the batsman hits the ball, then the ball starts moving in a different direction. It can change the shape or size of an object. If we squeeze a ball or squeezy ball or press a balloon, air-filled balloon, we see that the balloon changes its shape. Now let's go to motion. There can be two types of motion. One is translatory motion. And another is rotational motion. And there can be combination of the two motion at the same time. Translatory motion means if we move a body, for example, we have a object on the floor or on the table, we have a book on the table. If we push it, we will see that it just moves or slides on the table along the direction of the force. This is called translatory motion. Again, if we have any fan, for example a ceiling fan or a table fan, we see that the blades are rotating like this. So that is rotational motion. The best example of translatory plus rotational motion will be if we roll a ball on the floor, we will see that like this. So we will see that this is rotational motion. The ball was just rotating. If we push a ball on the floor, we will see that the ball moves forward and also along with it the ball rotates. This is the perfect example of translatory plus rotational motion. Okay. Now moment of force. Whenever there is a rotational motion along a fixed pivot. What is a pivot? If we have an object like this and we hang it from this position, we pin it here and we give it a force here, so the body will move like this. Okay, right? So there will be a moment of force or turning effect of force on the body, which is also known as torque. So there is a measurement, we can measure that moment of turning effect or torque on the body. What is that? Moment of force is the force applied, the magnitude of the force. For example, 1 Newton or 2 Newton, whatever be the force, the magnitude of the force multiplied by the perpendicular distance from the pivot, from where the body is suspended or fixed. That may be, that is the unit of length. It may be meter. The SI unit is meter. It can be also measured in centimeter or millimeter, like that, but the unit is, SI unit is meter. For example, it is 1 meter. So the moment of force will be the force multiplied by the distance from the pivot. In this case, it is the force F into OP, and the unit will be Newton meter. This is the SI unit of moment of force. For example, in this body, we apply the force. As we see here, the body moves along, the rotates along this pivot, right? Let's move on the next slide. What is the definition of moment of force or torque? The moment of force is the product of the magnitude of the force and the perpendicular distance of the line of action of the force from the axis of rotation. I will again explain it here. The moment of force or torque is the product of the magnitude of the force. We have a body here. The body may be suspended or body may be horizontal also, whatever in position it is. In any position, the body, it's not only that the body is in a suspended position. The body may be in a horizontal position. The body may be in a angular oblique position, whatever be it. So if we put, for example, here, if we give a force, and this is the perpendicular distance from the pivot, from the center to the point of application of the force. So the moment of force will be this F multiplied by this distance D. It has to be kept in mind that moment of force is a vector quantity and it has direction along with magnitude. Likewise, we have already studied that what is the vector quantity? Vector quantity is anything which has got its magnitude and direction. For example, force is a vector quantity. So, torque or moment of force is also a vector quantity, because if we rotate it counterclockwise, this is the direction, so this is a positive torque. And if we rotate it, for example, we have a body like this, we have a body which is pivoted here, we have a body which is pivoted here. If we push it this way, so body will be turning what? Clockwise. So the moment or torque will be negative. We will consider the moment of force or torque as negative. But if we apply a force this way, the body will turn counterclockwise, and in that case the moment of force or torque will be taken as positive, So let's just read the definition. Moment of force is a vector quantity and it has direction along with magnitude. Anti-clockwise direction is taken as positive, whereas clockwise direction is taken as negative. Some common examples of moment of force in our daily life. We have a door here. We all open or close doors or windows in our everyday. So we have a door here, and the door is fixed at this point. This is the hinge, so this is the fixed point. This is the, or the pivot. This is the fixed point of the pivot. Now it will be our common experience, or you can experiment it now also, that if you put the force here at the this outer edge, you will see that it takes very less effort to open or close the door. If you put the same force here, not the same force, if you have to put more force to open or close the door, if you put the force at this point, like, just I will refer, this is the point A and this is the point B. It will take more force to open or close if you put the pressure or the force at point B, and if you put pressure or force on point C, you will see that it is impossible to open or close the door. We can do a quick maths out here. Now it takes a fixed amount of moment to open or close the door, just because of the friction. The factors are the mass of this door, the friction of the hinges and everything. So the moment of force that is required to open the door, open or close the door or move the door, is fixed. Let's assume, just it's assume it is 10 Newton meter. Just assume, just it's a wild assumption. And let us assume this direction from point A to the point B, not point B, to the hinge, it's 2 meter. 2 meter is long, huge. 2 meter door, it's rarely seen, but let us just assume from point B to the hinge it's 1 meter. Let's assume this point B is in the middle and C will be like 0, right? If you have any doubts, you can just mention in the comment. So let us calculate what will be the force required to open the door if we apply the force at point A. So what is the formula of moment? Moment of force is equal to force into multiplied by distance. So force will be moment multiplied by distance, divided by distance. Then since the moment is constant, I have assumed it to be 10 Newton meter, and I divided by, since the distance is 2 meter, I divided by 2, so I get the force as 2 meter, the force as 5 Newton. Now again I apply force at point B. So force at A, I denote it as force at A, and force at B will be, the moment required is the same, that is 10 Newton meter, divided by the distance, that is 1 meter, which it comes out to be 10 Newton. See, mathematically also we have derived that the force required if we put it at B will be greater, much greater. And if we calculate the force required at point C, we will tell that 10 Newton meter divided by 0 is equal to infinity or undefined, whatever you say. So you can never open the door when you put the force at the hinge. So we always, while opening or close the door, we automatically always the doorknob is fixed here and the doorknob is not fixed here or anything closer to the hinge, right? So let's move on. We have a spanner here, range, some, sorry, this is a spanner, some say. wrench which is used to turn a that nuts and bolts. So you will see that whenever we want to turn the nut or open the nut, we apply the force at the outer edge and not at this edge, because if the handle is long enough, we have a edge, we have an advantage, we have to apply lesser force. Here also, if we just do a small sum problem, for example, the moment that is required to open or close this nut is 10 newton meter. It's just an assumption, and the handle is, for example, 5 or 2 meter. Again we take 2 meter only for the ease of calculation, and this point is, for example, the middle point will be 1 meter. Now again, if we do the calculation as the previous one, we will see that if we put a force here, it will take us 5 newton, and if we take a force at the middle point, it will require 10 newton. So naturally we will be applying a force out here, right? Let's move on to the next. Again you will see that if we, while turning the steering, if you hold a bigger vehicle like trucks or uh, those tempos, all have a bigger, or bus rather, the bigger vehicles have a bigger steering wheel and the smaller cars have a small steering wheel. Is because just the bigger vehicles require more force to uh, turn the steering wheel. So a bigger diameter steering wheel will require lesser force. Now let's come to couple. Couple means what we know, or everyone know. Couple in our daily life, we know that two, husband and wife, right? So here also couple means whenever we are putting the, see, this is the pivot and it has got the length is same in the two sides of the pivot, and we are applying force on both the sides but on a different direction. But actually the direction is same, because if we put it this direction, it will be anti-clockwise, and if we put direction is this way, it will also be anti-clockwise. But if you see from top, we see that the forces are at a different direction. So this is called couple. See here, we are applying force here and we are applying force here. Both are in this diagram, both are at a anti-clockwise direction. So uh, both are at a clockwise direction. So the moment that is generated, or the torque that is given on both cases, are negative. Some daily examples, some common examples where we apply torque on daily are while opening the cap of a bottle, we apply force here and we apply force here, and the center is this. Well, this is the center. So if I just draw a line for reference, we'll see that this is the center and we applying a force here while opening, or we applying a force on the different direction while closing, whatever, but we are applying the same force here also and here also. So at point A and point B, so it's a couple. While opening or closing a tab, this is the pivot, and we are applying force here and we are applying force in this direction. So this forms a couple. Here also this is the center. This is the center or center line or pivot, and we turning a key and we apply force with our fingers on both the sides, right? Now what is the moment of couple? Moment of couple is force applied multiplied by the perpendicular distance between the application of the two forces, the total this direction, this distance. This is the, if we take it d, so moment of couple is only one force. It is not that f plus f into d, it is only f into d. So if we just do a quick derivation, moment of force at end a, this is the end a, is equal to, and this if we take it as o, moment of force at end A is equal to F into OA, right? And moment of force at end B, this is the end B, is equal to F into OB. Now, since both are anti-clockwise, both are in the same direction, so we will be adding up the total moment. If you want to calculate the total moment, we have to add up. So we are adding up, total moment is F into OA plus F into OB. We take force as common and we get F into OB plus OA. But OA plus OB is nothing but AB. So F into AB. Therefore, we can deduce that moment of couple is equal to either force into perpendicular distance between the two forces. For example, when we are turning a cap with our fingers, so every finger is applying a force of say 1 Newton. Here also 1 Newton. So the total force will be 1 Newton multiplied by the distance between our fingers. Right? Got it? It will be either force. Now let us come to equilibrium of force. What happens in a tug of war? Whenever there is a tug of war being played, so there are lots of people out here, they are pulling it, right? Here someone pulls it, and here this way also pulls it. So someone is pulling it this way and a team is pulling it this way. Now when the force applied by both the teams are equal, if both the teams have the same strength, so you will see that the center point or that reference point, they attach a handkerchief or something just to point, it will not move this way or that way. Okay, so this forms a static equilibrium. Means even if there is force, it's not moving. For example, if we have a cup here and we apply a force of 10 Newton this way and we apply a force of 10 Newton this way, so you will see that the cup will not move. Right? So this is called static equilibrium. Here also, if we consider according to the moment, when if two kids are on a seesaw, for example, and both are of the same weight, so you will see that the seesaw remains like this. It's not going up or going down. So we can say that it's in a equilibrium. The force applied here and the force applied here, and if it remains in this same position, So this is the equilibrium of bodies. We will be equilibrium of moments we will be discussing at a later slide. It's just a overview. Now there is dynamic equilibrium. What is dynamic equilibrium? When one force is greater, for example this is 10 Newton and here this is 5 Newton. So we will be seeing that of course the body will be sliding this way. But the body will be mm, going or sliding at a constant velocity, right? There will be no acceleration of the body. Then we can tell that the body is in dynamic equilibrium. The body is sliding but there is no acceleration, so there is a dynamic equilibrium. The best example of dynamic equilibrium is if we drop a body from a very large height. For example, the body is coming down. First of all, there will be acceleration of the body. What is the rate of acceleration? It will be 9.8 meter per second square. Now, after some time, the body accelerates from zero. First of all, when we drop the body, the velocity of the body will be 0 meter per second. The velocity. Now, after some time, the body, for example, just we assume the body assumes a velocity of 10 meter per second. Now that is the acceleration point, but after some time this velocity becomes constant. The velocity won't increase. It attains a terminal velocity. Terminal velocity. Just because of the drag force of the body or the air resistance, there is a drag offered to the body by the air. So after some time it attains a terminal velocity and the uh, velocity becomes constant. Here it attains, this is the perfect example of dynamic equilibrium. This frictional force, drag is nothing but the frictional force. Friction force offered by air. Friction by air. And this way the force is given by the gravitation. Gravitation. So the upward force is given by the friction by the air and the downward force is given by the gravitation. A time comes when this frictional force, upward frictional force, becomes the same with the as the gravitation force downwards. So the body attains a dynamic equilibrium, right? Conditions for equilibrium. The resultant of all the force acting on the body should be equal to 0. What is the equilibrium? Whatever it may be, dynamic equilibrium or it may be static equilibrium, the resultant of all the force acting on the body should be equal to 0. The algebraic sum of moments of all the forces acting on the body about the point of rotation should be 0. So here it's a simple force equilibrium. For example, a body is here, one man is pushing it this way, one man is pushing it this way, and both the forces are same, 1 Newton, 1 Newton. So it will be in a static equilibrium, or as we just studied, if it is falling down but the velocity remains the same, there is no acceleration, so it will be in a dynamic equilibrium. And in a the perfect example I can tell is the beam balance. For example, this is a beam balance. Whenever we go to the market, we can see that there is a beam balance. The man puts up, for example, 1 kg bar here, 1 kg weight here, and the it puts some vegetables here. First we see that whenever just the moment he puts the 1 kg weight here, it comes this way. This drops and this goes up. But as and when he puts the vegetables, we see that this bar becomes horizontal. And at the point when this bar becomes totally horizontal, that is the point when the vegetables has the weight of 1 kg equal to this weight. So this is the point where the moment is this side moment is equal to this clockwise moment. This clockwise moment is equal to the anti-clockwise moment. So at this point this beam balance attains equilibrium. It is neither moving this way, it is neither moving this way. This is the point or the state where the sum of the moments of all the forces acting on the body about the point of rotation, this is the point of rotation, is 0. Right. You can also do a simple experiment here. Right. For example, you can take a ruler and you can take a 1 kg, hang a 1 kg bar here at this outer edge. At this, for example, this is the 7 inch, 7 cent. This is the 15 or 16 centimeter, for example. Let's assume this is the 16 centimeter end, and you hang a stone. We don't know the weight of the stone. Okay, we can calculate. We can calculate the weight of the stone from here. For example, the weight of the stone is x kg. Right, and then what you do, you attach a string in the middle and you hang it from here with your finger, and then you will see that the ruler is bending either this way or bending either this way initially. Now you slide this point, you can slide it this point or this point such that it attains a, you will see that the ruler becomes horizontal. It neither points this way or neither goes anti-clockwise. That is the point, that is exactly the region where the moments, this is the what? Clockwise moment. Sorry, this is the anti-clockwise moment or the positive moment, and this is the anti-clockwise clockwise moment or the negative moment. They have attained equilibrium, they have become equal. Okay, so at that point, what is the, let's do the simple sum here. We have taken it to be x kg, we will find out what is the weight. Let us assume this length is uh, 9 centimeter. So this length will be, this will be 16 minus 9, this will be 7 centimeter. At this point the ruler has attained a equilibrium, it's not going this side or going this side. So what is the anti-clockwise moment or the positive moment? It will be 9 into x Newton meter. And what will be the clockwise moment or the negative moment? It will be 7 into 1 Newton meter. Right, sorry, I have just made a mistake. Let's assume this to be, we are not going into this to be 1 Newton force, and this to be not x kg, this to be x Newton. Right, this to be x Newton for the sake of simplicity, because we can convert it to, from just we have to divide or multiply by 9.8, which is the acceleration. So just we are not, we are just studying moments here, the principle of moment. So we are not going, for the sake of simplicity, and ease of calculation, we instead of going by kg, we directly go by the force. We take by Newton, not by kg. Okay, so this is the positive moment or the anti-clockwise moment is 9x Newton meter, and the negative moment or the clockwise moment is 7, so it will be 7 Newton meter. Now in equilibrium this should be equal at equilibrium, so 9x is equal to 7 Newton meter, or x is equal to 7 by 9 Newton meter. So 7 by 9, let's calculate it. What is 7 by 9? It will be 0.77 approximately, is equal to 0.77 Newton. So we can tell that this x, the force, is 0.77 Newton. When we will be doing sums on it, we will be doing both with force and with kg or weight. So then it will become clear how we can interchange between weight and force. But here we will be just seeing, we since we are just developing the concept, we will be taking as Newton. Okay. So this will be 0.77 Newton. We can calculate it this way. So let's move on. Here also we see that, okay, the principle of moments. According to the principle of moments, according to the principle of moments, if the algebraic sum of moments of all the forces acting on the body about the axis of rotation is 0, then the body is equilibrium. In earlier example, we just worked with two forces, one on the left side and one on the right side. But we can have as many as forces, means the forces will be 100,000 trillion billion anything, the number of forces that we can work with. Here we see that we have two forces this side and two forces this side. We can have also another force, I can add another force this side also. Now what is the moment for this weight A? This will be this direction to this distance dA, I just name it dA, into this force FA. What will be the moment? This will be the positive moment or the anti-clockwise, since it's pulling it anti-clockwise, right? So what will be the distance? Let's assume this distance to be dB, this weight is B, and this force applied by this object B is FB. So what will be the total moment in the left hand side, or the positive moment or the anti-clockwise moment, whatever you say? This will be FA into dA plus FB into dB. Likewise, if we tell this as C, this as D, this as E, and this moment will be this distance as DC. For example, this distance is DC, this distance is D suffix D, and this distance is D suffix E, D suffix E. So we will have FCDC plus FDDD plus FEDE. And this will happen when, and whenever this happens, means this entire equation is satisfied, then only you will see that this bar is not moving. This is in a horizontal position, right? Or it is in a equilibrium position. According to the principle of moments, if the algebraic sum of moments of all the forces acting on the body about the axis of rotation is 0, then the body is in equilibrium. Here also we see that it is a body, it is arbitrary body. Any body you can take it. It's called a lamina. Right, it is called a lamina. You can just make a body lamina, you can create in your home also. You can just take a, there can be two types of bodies, right? One can be a regular body, for example a square. You can do this experiment also at your home, or we can do this experiment online, means on the video I will post this experiment the next day, right? Or you can take a circular body. These are all regular bodies. Or you can take a let's see, we take a triangular body. So these are all regular bodies. This is an equilateral triangle, you can do it. And we take a irregular body. This is called a lamina, right? So in these regular bodies you will see that the center point is the geometrical center, the center of equilibrium. For example, if you hang it like this, if you put a pin through it, through this point, you will see that the body rotates this side, right? If you put a pin through this and release it, you will see the body will rotate this side. Here also in this triangle also, if you put a pin through this and just leave it, you will see that it rotates this way. Got it? But if you put a pin through this, you will see that the body, the square of thing, will remain in a constant position, equilibrium position. Even if you rotate it, it will stay in that position only. Here, if we put a pin or any sharp object through this, and if you leave it, even if you rotate it by your hand, you will see that it remains in that position only. It does not change because it is in a equilibrium. In the circle, if you put anything through here, this is a, you can make it through but just by cutting a cardboard. You will see that if at the point when you leave it, you will see that it body rotates by itself. But if you put it through the center, perfect center, you will see that the body does not rotate. Even if you move it by hand, it will like stay like that only, because it has attained equilibrium position. Why? Because this body is can be considered, I will draw it here. For example, this body, this lamina, the center point is this. Okay, the center point is this. Let us assume the center point is this one. So this body is composed of very small molecules. They are called particles or molecules. Or so now every molecule can be considered as a different body, different weight. They have their own weight, and they are exerting moment to them. Moment, right? They are having their own turning moment. Some bodies are having the negative, sorry, this one is the positive or anti-clockwise turning moment, and some of these particles are having clockwise turning moment, negative turning moment. Now whenever the total sum of the positive moments is equal to the total sum of the negative moments, the body becomes at equilibrium. The body does not move either this way or this way. Now if we, just as we talked, if we have this position, for example we take the lamina, and we hang it at this position. This is the point. Now most of the particles, see, the most of the particles are the left side, right? And they are exerting a positive moment, and very few particles are there which are at the right side. Now obviously the sum of the positive moment, this is the, yes, the sum of the positive moment will be less more than the sum of the negative moments. So the body will turn this way. They are not acting in equilibrium. There is no equilibrium at this position, so they will turn so that the lamina comes at this position. Now at this position they have attained equilibrium, because now all the particles are having this force this way due to the gravitation, and these particles are also having force this way. Now if we again measure the clockwise and the anticlockwise, now we will see that the clockwise is equal to the anticlockwise, so they will be at a equilibrium, right? So we can do this experiment, and so this we will end the video at this point. We will be continuing with the moments and the other portions of the chapter in the next video, because it will become a very long video then. So please subscribe, and if you have doubts, again I am telling, if you have doubts, you just comment me and I will explain it to you. Okay, thanks for being with me. Wish you all the best. Bye.